So the one of the most important factor that affect the rate of a chemical reaction is the concentration of the reactants. Now here yesterday we have seen the law of mass action. What is law of mass action? The rate of a reaction if A moles of A reacts with B moles of B to give products. This is the reaction. A moles of A is reacting with B moles of B to give products. So what is rate is equal? Rate is proportional to, according to law of mass action, rate is proportional to molar concentration of A raised to A into molar concentration of B raised to B. This is according to law of mass action, or rate is equal to a constant K into molar concentration of A raised to A into molar concentration of B raised to B. That is, the K is called the specific rate constant. If A is equal to molar concentration of A is 1 and molar concentration of B is equal to 1, then we can say rate is equal to K, or we can define rate constant as the rate of a chemical reaction in which the concentration of the reacting species is unity. So this is according to law of mass action. Now, we know that for a chemical reaction, the reaction takes place by the collision between the molecules. So here it means that molecules of A and B molecules of B collide with each other and we get the products. So the total number A plus B is called the molecularity of a reaction. It is called molecularity of a reaction. So molecularity of a reaction we will get by adding the coefficients in the balanced chemical equation. Coefficients of the reactants. If you add, you will get the molecularity of a chemical reaction. Consider the reaction N2 plus 3H2 giving 2NH3. For the manufacturing of ammonia, this is the reaction. What is the molecularity of this reaction? 1 molecule of nitrogen and 3 molecules of hydrogen collides with each other to form ammonia. So molecularity of this reaction is equal to 1 plus 3, 4. Understood? So this is molecularity of a reaction. Now, according to collision theory, it means the 4 molecules, that is 1 molecule of nitrogen and 3 molecules of ammonia collide with each other and we get the product. Understood? Now, but you see one reaction I will write. H2O2, dissociation of H2O2 in presence of iodide ion gives H2O to H2O plus O. This is the reaction. 2H2O2 dissociates to give water and oxygen in presence of iodide ion. Now the rate, experimentally we determined the effect of concentration on reaction rate. We have seen that rate is equal to K into molar concentration of H2O2 into molar concentration of I minus. Actually, according to collision theory, what must be the rate constant? Rate constant is equal to, or rate is equal to rate constant K into molar concentration of H2O2 square. We must get this one. But actually, experimental determination show that the rate is proportional. Rate is equal to K into molar concentration of H2O2 into molar concentration of I minus. Only one molecule of H2O2 is remaining in the equation or in the reaction. So a mechanism was proposed, or it was explained that the reaction is taking place in different steps. In first step, H2O2 plus I minus will give you H2O plus IO minus, and in the second stage H2O2 plus IO minus gives H2O plus O2 plus I minus. So the first step, one molecule of H2O2 reacts with I minus to give H2O plus one intermediate, that is IO minus, H2O2 plus IO minus in the second step reacts again to give one molecule of H2O, one molecule of oxygen and I minus. What is the net reaction taking place? Net reaction, you can see that these two cancel. Then IO minus cancel. You write 2H2O2 gives 2H2O plus O2. So we got only the net reaction, but actually that reaction takes place in two steps. You see, the first step, that is the step in which the reactive intermediate is formed, that is a slow step. And this reaction in which the reactive intermediate is reacting, it is a fast step. So the first step is a slow step and the second step is a fast step. And the slow step, you know that if a thing is or if a process is carried out, the one which is reacting very slowly, that will determine the rate of reaction, isn't it? The whole reaction can proceed only if that slow change is happening. So here also one step is a very slow step. So rate of reaction depends on this slow step. So the rate of this reaction is depending only on the concentration of H2O2 and I minus. So in the experimental, this is the correct thing then. So the rate of reaction is proportional only to H2O2 and I minus. So this is experimentally what we determine. So this expression is called a rate law. Rate law. This rate law gives you the actual dependence of the concentration terms on the rate of reaction. How the rate is depending on the concentration of the reacting species. Actual dependence is shown by this rate law. It is determined experimentally. Now, what is the power of H2O2 here? And power of I minus is 1. And we call this the power of the reacting terms or reacting substances in the rate law as order of the reaction with respect to that reactant. So order of the reaction with respect to H2O2 is 1 and order of the reaction with respect to I minus is 1 and overall order of the reaction, order is equal to 1 plus 1, 2. So this is overall order of the reaction. So order of the reaction is the sum of the powers to which the concentration terms are raised in the rate law equation. It is that what is the rate law equation? It shows the actual dependence of the concentration of the reacting species on the rate of reaction. Understood? So that means whole as molecularity we are getting from the balanced chemical equation. That doesn't mean the rate of the reaction actually depends on the concentration terms raised to the power of their coefficients in the balanced chemical equation. Understood? So a reaction in which if these many molecules will have to collide with each other to form the products, such reactions will take place in different steps. Those reactions which are taking place in different steps, we call those reactions as complex reactions. Those reactions which takes place in different steps are called the complex reactions, and the steps in which they are doing it, those steps are called elementary steps. And writing steps like this we call writing mechanism of a reaction. This is called the mechanism of a reaction, that is how the reaction is carrying out. That we explain by showing the different steps. And in different writing like this in different steps of a reaction, that is called mechanism of a reaction. Now certain reactions take place only in a single step. Those reactions are called elementary reactions. Elementary reactions. Some reactions are elementary reactions which takes place in only one single step. Some reactions like this, they take place in different steps. So that reactions are called complex reactions. And in those complex reactions, the slowest step will be the rate determining step. And when we are writing the rate law, we take the concentration of those reactants which appear in the slowest step. Understood? Though we consider only those molecules which take part in the slowest step. Other one equation I will tell you. One more example. One reaction is the 2NO2 plus F2. 2NO2 plus F2 gives 2NO2F. A reaction is there. 2NO2 plus F2 gives 2NO2F. What is molecularity? 2 plus 1, and we expect that rate of reaction is equal to K into molar concentration of NO2 raised to 2 into molar concentration of F2. This is what we expect. But actually, experimental determination shown that this is wrong. It shows that the actual dependence is rate. Experimentally, it is determined that it is equal to K into molar concentration of NO2 into molar concentration of F2. Molar concentration of NO2 into molar concentration of F2. So, molecularity is 2 plus 1. But here order with respect to NO2 is 1 and order with respect to F2 is 1 and overall order of the reaction is equal to 2. Understood? So, this is a second order reaction. Sometimes this is again a complex reaction in which the reactions are taking place in different steps. So, this is one, the step which is the slowest step we taken as the rate determining step, and we have taken only concentration of those reactants. Understood? Now, so in some cases molecularity can be equal to the order of reaction if it is an elementary reaction. In complex reaction, the order of reaction will be different from that of the molecularity. Understood? But molecularity doesn't show the actual dependence. Only order of the reaction is that is the power to which the concentration terms are raised. That alone shows the actual dependence of reactions rate. Now, the order we are experimentally determining it. Experimental determination, we will find out how the concentration of NO2 affects the rate of reaction, how the concentration of fluorine affects the rate of reaction, and we find out the order of reaction with respect to NO2, with respect to fluorine, and we find out the overall order. So, this is an experimental quantity, whereas molecularity is only a theoretical one. We are taking it from a balanced chemical equation, believing that these molecules all are taking part in chemical reaction. Understood? So, this is molecularity, then molecularity is only a theoretical quantity, whereas order is an experimental quantity. Understood? Order we are getting from the rate law, which shows the actual dependence of rate of reaction. Understood? Now, but molecularity, we are simply adding the number of molecules which are taking part in the chemical equation from the balanced chemical equation. Right? Now, this molecularity cannot be fractional, but order can be fractional. Order of a reaction can be 3 by 2 like that. For example, H2 plus Br2 gives 2HBr, a reaction. We think that molecularity is 1 plus 1, 2. But the experimentally it is determined that rate of reaction is equal to K into molar concentration of H2 into molar concentration of Br2 raised to half. So what is order? 1 plus half, that is 3 by 2. 3 by 2 is the order of the reaction. This is experimentally what is determined. This is what is we are writing a balanced chemical equation. Understood? So here order can be fractional, but molecularity can never be fractional. Understood? Now order can be even equal to 0. That means for dissociation of ammonia on surface of platinum to NH3, it will dissociate to give N2 plus 3H2. See, for this reaction, as the time goes on, usually when rate decreases, when concentration of the reactant goes on decreasing. But here, whatever may be the concentration of ammonia, the rate is the same. That means rate is independent of concentration of ammonia. Then how will we write? Rate is equal to K into molar concentration of NH3 raised to 0 because it is independent of the concentration of ammonia. Independent means this term does not come. NH3 raised to 0 means 1. So NH3 raised to 0. That means the order of the reaction is 0. So order of the reaction can be 0 if the rate of reaction is independent of the concentration of the reactant. There are certain reactions like that also. So order can be equal to 0. Molecularity can never be equal to 0. Understood? So these are the differences between order and molecularity. Order is an experimental quantity. So now onwards we will fix only the order. We will talk about only the order of a chemical reaction. Molecularity has no significance here because molecularity shows only the number of molecules which takes place in the overall reaction. That does not give you the actual dependence of the concentration on reaction rate. Okay.